This problem relates directly to Graham's law of diffusion because it uses the law core idea that Graham law states that the rate at which a gas effuses is inversely proportional to the square root of its molar mass. In a simpler version, that means that the problem is a direct application of Graham's law because it uses the relationship between the effusion rate and molar mass to identify an unknown gas.
So the relevance of my problem to the real world. I chose a problem that involves carbon monoxide and an unknown gas. I chose carbon monoxide because that's something that is very common. It's released by furnaces and engines. It can become very deadly. The other gas I chose to use in my problem is an unknown gas. I chose an unknown gas because that gives you the chance to use Graham's law to determine the molar mass of the unknown gas, so you can actually find out what it is in the end.
Alrighty, the relevance of the problem for Graham's law of diffusion. Graham law helps us understand how different gases effuse or escape through small openings at different speeds depending on the molar masses. Earlier in this project, we explored gas behavior, molecular motion, and
This problem forces students to understand the relationship between molar mass and diffusion rate. Lighter gases move faster and heavier ones move slower. This is the core idea behind Graham's law. This problem shows how the law applies in the real world, such as in diffusion, gas separation, or predicting gas behavior.
The benefit of my problem is that it associates Graham's law to real world problems like carbon monoxide mixing rapidly with the air that you're breathing if there's a leak indoors. Explains why it becomes dangerous so quickly, and it also makes you realize why CO detectors are so important.
benefits of the problem. Understanding this, Graham's law problems help students see how the mass of gas particles affect the speed of fusion. This benefit is important because it connects molecular mass to real world applications like gas leaks, respiration, environmental science, and laboratory gas behavior. By working with actual numbers, the learner builds confidence using formulas that explains how gases have in different physical situations.
How I made my Graham's law problem. So I made this problem by picking hydrogen as the gas that we already know about, comparing it to an unknown gas so there'd be something to solve for. I chose an easy number, hydrogen being 4 times faster, because it makes math simple. I just made sure that the condition fits Graham's law and checked the answer to see if it made sense. That's basically how I came up with the problem. Why the problem isn't too simple to be useful. So even though the numbers in the problem are easy to work with, it still helps you understand the real idea behind Graham's law. You have to compare two gases, use the rate ratio correctly, plug everything into the formula, and solve for the molar mass of an unknown gas. This means that you are not just memorizing the law, but you are actually applying it. Why the problem isn't too difficult to be useful. Since the numbers are simple, the ratio is easy to work with, and it only has one variable. The molar mass of the unknown gas needs to be solved for. This keeps the math manageable while still requiring you to use Graham's law formula correctly. What difficulties I had writing a new problem? It was really hard, but if the rate ratio is unrealistic or if the molar masses don't match up, the problem will not solve clearly. You have to think about what we're supposed to figure out, like the molar mass or the rate, and set it up so the question has a clear answer. Some of the things that I avoided making the problem unrealistic or impossible to solve, which can happen if the rate ratio and molar mass do not line up with Graham's law.
When I was developing this problem, I wanted to use a situation we hear about every day. So I started by choosing the original gas that I was going to use, which was carbon monoxide. I chose to have a fixed distance that allows rate comparison, and the time delay immediately it suggests that there's a difference in diffusion rates, and you can calculate the molar mass of the unknown gas and reveal hidden information.
The development of the problem is to create this brand new Graham's Law. I started by choosing two gases that have significantly different molar masses, neon and oxygen. Then I selected a realistic diffusion rate for neon, which allowed for a meaningful calculation when applying the mathematical formula. The numbers were chosen intentionally so the math would not come out overly simple or produce unrealistic decimals.
Information and steps I added to make my problem different. I added the idea of identifying an unknown gas based on its molar mass, which makes the problem feel more like a real investigation instead of just a math exercise. By choosing hydrogen as the known gas and keeping the numbers simple, I created a problem that is easier to follow but still requires understanding of how Graham's law works. A lot of problems online include multiple gases, tricky decimals, and additional information that I don't believe is actually needed, but mine keeps the focus on the key of Graham's law, and I also purposely chose to use an easy to use rate ratio. How my problem goes above and beyond common problems. So since my problem is simple, focused, and thought out, so it teaches the idea behind the law, not just the formula, so we can clearly understand. Overall, it shows more intention and clarity than many basic problems found in textbooks or online.
The uniqueness of my problem is both of these gases naturally diffuse in the air that we're surrounded by. Since they're both found in air, comparing their diffusion rates is realistic and relevant to everyday life. When you start out not knowing what gas X is, you can determine the type of gas after solving the problem and determining the molar mass of it. It shows the relevance of using Graham's law in real-world situations.
The uniqueness of the problem, my brand new problem, is noticeable different from typical textbook or internet examples because I created from scratch and added specific steps, context, and details that are not found in common problems. Unlike standard problems that usually follow predictable patterns, mine include unique numbers, a realistic scenario, and an extra layer of reasoning that requires deeper thinking.
In this data set, the effusion rate and molar mass are connected through an inverse square root relationship. This means lighter gases move much faster, but as gases get heavier, the speed drops more slowly.
For the visual for my problem, I chose to go with a bar graph. It shows the two gases. You have your carbon monoxide and gas X, and it shows their diffusion rates, and you have it showing that the carbon monoxide diffuses at a higher rate.
So the visual for the problem is to illustrate the relationship between gas molar mass and effusion rate. I created a table to show the effusion rates of several gases using Graham's law.
The symbol means R1 equals the rate of effusion of gas 1, R2 is the rate of effusion of gas 2, M1 is the molar mass of gas 1, and M2 is the molar mass of gas 2. You can also use the rearrangement to solve for molar mass, which is M1 over M2 equals R2 over R1 cubed. Or if time was used instead of rate, you can use T2 over T1 equals the square root of M2 over M1.
The formula for my problem, first you have to find the diffusion rate, and then you're going to use Graham's law to find the molar mass. So you have Graham's law, you have your R2 divided by R1 equals the square root of M2 and M1.
The main formula used to solve this problem is Graham's law of effusion. The formula shows that the rate of effusion is inversely proportional to the square root of the molar mass, so lighter gases effuse faster. The units for rate at milliliters per second and molar mass is in grams and molecules. Using this formula, we can calculate unknown effusion rates if one gas rates and the molar masses are unknown.
Hydrogen gas and an unknown gas are allowed to effuse under the same conditions. We noticed that hydrogen effuses 4 times faster than the other gases. To solve this, we use Graham's law, which compares the rate of effusion to a molar mass. The equation is rate 1 over rate 2 equals the square root over mass 2 over mass 1. Whenever you plug in the numbers, you're going to do 4 equals the square root of the unknown molar mass divided by the molar mass of the hydrogen, which is about 2 grams per mole. Square both sides to remove the square root. That gives me 16 equals the unknown molar mass divided by 2. Then I multiply to get 2 and get about 32 grams per mole. A gas with a molar mass of 32 is more than likely oxygen.
So the solution for my problem. First, you're going to find the diffusion rate ratio using the time. So you're going to divide 40 by 32, and that's going to equal 1.25. That means carbon monoxide diffuses 1.25 times faster than gas X. Then you're going to use Graham's law to find the molar mass. So you're going to divide the square root of mx over 28, which is going to mean that the molar mass of X is going to be 43.8.
The solution for the problem, the diffusion rate of oxygen gas is 4.92 milliliters per second. To figure out how fast oxygen gas diffuses, I use Graham's law, which compared the rates of 2 gases based on the molar masses. Since neon is lighter, it moves faster, and oxygen being heavier moves slower. The formula is R1 over R2 equals square root of M2 over M1.
To verify my answer, I plugged the molar mass I found back into Graham's law. I did square root of 32 over 2, and that gave me 4, the same rate ratio I was given before. And since the calculations matched the original information, I confirmed that my answer was correct. The unknown gas is heavier than hydrogen, so it makes sense that hydrogen infuses faster. My answer, 32 grams over mole, maxes oxygen, a common gas. And the rate ratio of 4 also makes sense, so the answer is reasonable. And this solution process is valuable because it shows how Graham's law connects measurable rates to molar masses. By observing that hydrogen infuses faster, I can identify the unknown gas and confirm my results. Following a step-to-step method builds problem-solving skills and provides clear scientific approach, which supports the goal of our project.
Verification for my problem. So to verify it, you're going to check each step against the rules of diffusion. So both gases travel the same distance. That means that the gas that arrives faster must have a higher diffusion rate. When you cross-check this with the molar mass calculated, gas X arrives later, so it does have the higher molar mass.
Okay, and last but not least, verification for the problem. Does the answer make sense with the concept? As I said before, neon is lighter than gas. Lighter gases always diffuse faster, so oxygen rate should be less than neon's rate. And the numbers are in the right range, and also the units are very consistent.